everyone, welcome back. So today we're going to talk about unbounded sets. So I know if you watched my last video about bounded sets, we did talk about the definition of unbounded sets, but we'll do a reminder. If you don't know what the Archimedean property is, or AP is, then you're going to want to watch one of my old videos on that. So, okay. So let's recall, if X is an unbounded set, then for all M in the positive reals, there exists some element in there such that the absolute value of X is bigger than M. Okay? So you pick any bound. So let's say some evil scientist hands you a bound. You can always hand them back an element that's in X whose absolute value is bigger than that bound. Okay, that's what it means you're unbounded. Nothing bounds you. Okay, and remember the negation of this is a definition of bounded. So that's really important information. Remember, when you're going to do a proof about something like this, about bounded or unbounded, you want to state the definition somewhere. But since I am stating it here, and I have the luxury of not doing homework right now or a test, I'm not going to keep writing it for every proof I do. Okay, so let's start off with, let's jump right into a problem. So let's say X is natural numbers. Show X unbounded, okay? All right, so proof. So this one, it's kind of hard sometimes to think about how we could always show this. Sorry, I don't know a better way of saying that. So what often happens is what you do is you do it by way of contradiction. So you assume that there is a bound, and then you show, ooh, I can find something bigger than that. And then, and then you show that it's unbounded, okay? But remember, you don't pick a specific bound, you just say a general bound. So by way of contradiction. Or you could say proof by contradiction, either one is fine. So we're going to assume X bounded. So what does it mean to be bounded? Then there exists some M in the positive reals, such that for all elements in X, the absolute value of X is less than or equal to M. Okay, so that's just the definition of being bounded. So now we might want to think to ourselves, well, all right, what tools could we use to show that this is not possible? Okay, so we've fixed our M, although it's just a generic one. So you could plug in 1, you could plug in 22,043. So you're not picking a specific number, but you are sticking with M. Right? So M's not changing. We've fixed M. M's not changing, but we didn't give it a specific value. So now M can be anything within the real plus, but we fixed it for right now. Okay? So what tool can we use? Well, hopefully you're thinking about AP, because that's like one of the only tools that we have right now. So let's see, what does AP give us? Well, it gives us a natural number that's bigger than a real number. Okay, well, that sounds very useful right now. Okay, so by Archimedean property, there exists some capital N in the naturals, such that N is strictly bigger than M, since M is in the reals. Okay. So how does that help us? Well, since N is in the naturals and the absolute value of N equals N, so we have absolute value of N. Here, let's start it like this. N equals absolute value of... Sorry, I keep changing my mind. You don't have to write this last step here, but it does kind of like sum everything up pretty nicely. Okay, so, oh my gosh, I wrote it the wrong way. This is why you always have to be constantly rereading yourself. It's just so easy to just, you know what you're talking about up here, but you don't always write the things that you're thinking about. Okay. All right, why is this a problem? Well, we said that for all elements in our set X, that absolute value of X was less than M. Contradiction. You can't be bigger than M, but also less than M. Oh, sorry, less than or equal to. So that doesn't work. Therefore, X is an unbounded set in this case. Okay? All right, end of proof. Okay, so sometimes you'll see questions like this. So we're defining some set, we're handing you some set, and now you have to discern, is it bounded or not bounded? And then if so, you need to prove. You need to prove it. So if it is bounded, you need to prove that it's bounded. If it's not, then it's not. So I'm hoping that maybe you see that this is not bounded for more reasons just than that's what we're talking about today. But so answer no. Now let's do our proof. So, okay. I'm going to start by contradiction. So let's say proof by contradiction. Okay, so assume y bounded. Then once again, there exists an M. So remember, you don't have to use these letters. You could pick pretty much any letter that you want. I would stray away from the letters like O. But, yeah. Okay. And then there exists an M in the positive reals, such that, for all we can call them little y in our set, absolute value of y is less than or equal to M. Okay, all right. So now let's start. Okay. So maybe we don't really know where to go from here. My suggestion would be scratch work. But here is the problem. Okay, so maybe you try scratch work and you're still not going anywhere, and maybe you're in an exam so you want to move on to a different problem. So something that you could do, am I recording? Yes. So something that you could always do is you could always say, by AP, there exists an N in the naturals such that N is bigger than M. So that might not always be extremely useful, but maybe you'll get points for it for mentioning AP, and maybe you even put in the definition of AP or something somewhere. So, okay. So what would we do in the scratch work? So we want to first start by assuming what it is that we want. And so remember, I know everyone's heart just skipped a beat, but we're just in the scratch work. So that's all that we really need. In the scratch work, it's okay to assume what we want. All right, so what is it? So I want to assume that we have, maybe I'll call it little m or something, is bigger than, okay? All right, so now we have, so what do we know about 1 over 3m? Can that ever be negative? No, it cannot. So that's equal to just that. Well, we could write it as 3 to the negative m. We want that to be bigger than capital M. Okay. All right, so I know I can get an n bigger than m. If I have an n that's bigger than m, who can I make bigger than this that has to do with 3? Well, I could just do 3 to the capital N. This needs to equal 3 to the negative m. Okay, so then negative m equals, so what I really want is I want 1 over 3 to the negative n. Bigger than or equal to n. That is bigger than m. Okay, so is this allowed? Is this element in my set? Yes, it is, because n is allowed to range over all the integers. So if capital N is a natural number, then negative n is an integer, okay? Okay, cool. All right, so it looks like we go back into not scratch work, and we've already done part of the work here. We found our n bigger than m. That won't always happen. Sometimes it's like you need an n to be bigger than 1 over m or something crazy. You know, there's a bunch of different ways. You could even done the scratch work a different way, for sure. You could have just started doing some stuff with log and things. Stuff can get crazy really fast. Okay, So, all right, so we have an n bigger than m. All right, so let's say since n is in the naturals, then negative n is in the integers. So 1 over 3 to the negative n is an element in y, okay? So you always need to talk about why this element is in your set. All right, we know that n is less than or equal to 3n. You don't have to prove this, but maybe you could write in the parentheses next to it, induction, then m is less than n, less than or equal to 3 to the n. But we said for all y, contradiction. Therefore, y is unbounded. Woohoo! All right, box that up and ship it. All right. So I have one more example. Also, while I'm writing this example out, I would like to encourage anyone who can register to vote to please register. It's important that your voice is heard because your voice is important. Okay. And it's your local elections are very important as well as the national one. Okay. All right, so assume that it's bounded. Okay, then there exists an m such that for all x in our set, r minus q, absolute value of x is less than or equal to m. Okay. All right, so let's jump to scratch work. But what do we want? Well, we want an absolute value of x that's bigger than m. Well, unfortunately, we can't just get rid of the absolute value for all x, but we can just say there's always a negative version of whichever element that we choose. So we could just do that. That's fine. But I don't know. I feel like we have a bigger problem here. So rational numbers are known as you can make they're fractions made out of integers. So the numerator is an integer, the denominator is an integer. So if you're taking all real numbers and you're taking those away, the stuff you have left over is looking pretty weird, right? These are the irrational numbers. So what are some irrational numbers that we know? Well, two examples we have are pi and e. Those are two very commonly known ones. Okay, so let's think about, so looking ahead, and so this is kind of another trick, and I don't know how much I've talked about this semester, but I always teach students that it's kind of a rocking back and forth. Like you're looking at what you can use, so like what definitions you have, what the question's asking, and then you're also looking ahead. You're thinking about what's coming, right? And you just keep rocking back and forth, and that whole middle part is just rereading what you have and trying to elaborate more, okay? And you just kind of want to have that rocking back and forth type situation going. So here I'm thinking to myself, well, I'm probably going to want to use AP, okay? So if I use AP, what is AP going to give me? Well, it's going to give me a natural number. So natural numbers are integers in themselves, so it's certainly not going to be in the irrationals, right? You could always write it as that natural number over 1. Okay, so how could we take that natural number and turn it into an irrational number? Okay, let's think about is pi times y in r minus q. So here, sorry, if y is in the rationals, is pi times that in the irrationals. Well, you actually have all the tools that you need to prove this, but the way that I think about it is it doesn't matter if we can write y as a fraction. We can never write pi as a fraction, ever. So whatever we multiply by pi, can't write that as a fraction. Okay? Unless it's the inverse of pi. I meant any rational. Okay. Or 0. Ah. Yeah. So why not including 0? Okay. Alright. I think of all my little weird ways that this could happen. Okay. Yeah, I think so. So yes, this is true. Okay, so let's just find an n and then multiply pi by it. Because is that going to make it bigger? Well, pi is 3 point blah, blah, blah. Who cares after that? It's a positive number that's bigger than 1. So it's going to make, well, it doesn't even matter. You could even do negative pi because remember, we're going to do the absolute values. So as long as the absolute value of pi is bigger than 1, multiplication by that is going to make it even bigger. So awesome. Cool. All right, let's do what we came here for. By AP, there exists an n in the naturals such that n is bigger than m. Okay? Since pi is bigger than 1, then m is less than n is less than n times pi. N times pi is in the reals minus the rationals, since pi is in the real minus the rationals. Okay. All right, cool. So I know I'm writing the proof a little different, but remember, you can always change it up a little bit as long as it still makes logical sense and it flows in the correct order. Okay. So I couldn't just be done here. I need to explain why this is an element in the reals minus the rationals. Okay, so then m is less than absolute value of n times pi. But we said for all x in the irrationals, absolute value of x is less than or equal to m. Contradiction! Woohoo! The irrationals are unbounded. Please, 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 please don't forget to write your conclusion. Every single proof. So I know that we had a bunch of little different tricks that we used throughout, but the outline is kind of the same. So first we assume bounded. At least this is my way of doing it. This is not the only right way, but this is this strategy that I follow. So first I assume bounded. Second, I put an AP on bound, or on something that includes the bound in it. Okay, so now comes the tricky part. Use new natural number to get bigger number. Show why that bigger number is in our set. Conclusion, please. Conclusion. So I thought I would end with one that you can try on your own, and you can bring it to office hours or ask one of your friends who's also in the program. It's a set Z whose elements look like n squared over n minus 1. N being a natural number that's bigger than or equal to 3. Is this bounded? Prove why. So this one is kind of a step up, but I believe in you. Okay, see you next time.